Hello there. Today we're going to be talking about what is proofreading. Basically, proofreading is a way that mathematicians can talk to each other and explain how things work. So, you can find the truth and convince your friends of what you think the problem or solution is. Some key things about writing proofs is that it gives others deeper understandings of concepts, engenders logical and critical thinking, and allows you to make connections between concepts. Honestly, you can discover something that we believe is true, or help you disprove things that you didn't know wasn't true. So, moving on into the process, let's say you look at this, you say, oh, I'm convinced, I want to do more work into writing proofs. Well, proofwriting has a lot of rules. There are a lot of steps and just so many different things that you can get wrong when it comes to writing proofs, and it's kind of hard to conceptualize just by seeing this list here. So instead of going through each one of these things, we are going to show you how to write proofs by example. So this is our example here. We have our question, and then here is our proof down here. So first, let's go into the question. It says, let the function of t that maps to u be a continuous function. Prove that if t is compact, then f of t is also compact. When you're having proofwriting or questions, they'll start with an if statement here, and they will usually also have a then statement. So this is already true, and we're trying to use this to prove that that is also true. We have our proof here, and our proof is going to start with some assumptions, and then we're going to use some definitions and logic, theory, etc. to prove that then statement. Now we're going to go in depth over here and actually go through how we proved this. Before we go into our proof, go ahead, take a moment and look at this definition. It'll tell you what a cover is, an open cover, and what it means for a set to be compact. These are essential definitions before we get into our proof.
Let the function f, which maps t to u, be a continuous function. We're going to prove that if t is compact, then the function f of t is also compact. So we're going to let f be the set of all open covers such that alpha is an element of A. We're going to say that is an open cover of f of t, which is the codomain of our given function, f of t. Okay, so now let's consider G. We're going to define G to be the pre-image of U sub alpha, once again such that alpha is an element of A, and we can re-express G to be, we can say T, small t, is an element of large T, which is our domain, such that f of small t is an element of U, which is our codomain. So now we have t is in the set of our domain and f of t is in the set of our codomain. Now since our u sub alphas, which are our open covers, they cover u, we can say that there exists some alpha such that f of t, our codomain, is in the set of u, which is our given codomain, or rather u sub alpha, which is our open covers. And we can say that just by the definition of open covers. Thus, small t is an element of the pre-image of u, the pre-image of u sub alpha. And that gives us that G is an open cover of our codomain T. So now we know that T is compact, and that was given. T is compact. We know that it has a finite subcover. T has a finite subcover. Subcover, and we'll define that as the pre-image of all of our U sub-alphas. And we'll just use this notation, and that's U sub R. Use that notation to represent our covers. And now, therefore, our set of U's, which are the open covers that we defined earlier, to UR, is a finite subcover, is a finite subcover of f of t, which is our codomain U. So now we know that U is compact. U is compact.